I gave you an introduction to how are we going to calculate global stiffness matrix from single element stiffness matrix that we developed in MATLAB. So we developed the actual element stiffness function module the last week to calculate the stiffness matrix for a single element, which we did by using the Young's modulus of elasticity, area of element, and then the degree of freedom and the node vectors accepted as an input. So in today's session, we are going to discuss how are we going to input for a whole structure for a instead of doing it for a single element. So the function format is going to be same. So the last week we accepted the degree of freedom as an input. In this week we are going to calculate the number of degrees of freedom associated with the element by ourselves based on the knowledge that we gained in this session. So the input term degree of freedom has gone away from the input parameter. The node xy. Node xy is the x coordinate and y coordinate of all the nodes acting in your structure, which is similar to the term that we accepted as an input last week. Along with the node information, an additional parameter that we are going to accept as an input from the user is the elements vector. So why is elements vector necessary? Because elements vector is an input where you are conveying MATLAB which two nodes are connected. For example, you might have node 1 to 5 in your input parameter, but MATLAB needs to know which two nodes are connected to form an element. So MATLAB calculates length, orientation, everything by itself. But all you need to tell is what nodes are connected to form an element. And along with it, basically for at this point of time, instead of developing a separate function to accept the inputs from the text file, which might be slightly like the concept is same, but it's just like a fancy way of developing a function. I just wanted to explain to you the concept first, and then we can go on ahead in like structuring our script. So the inputs are going to be the node vector, elements vector, and the material properties, namely the Young's modulus of elasticity, and then we will have area associated with each member. So let's get started with step-by-step procedure on developing the function to calculate the global stiffness matrix. So the first step is to calculate the number of nodes. So the node xy has x coordinate and y coordinate. So for example, if you are giving a row vector and column vector with row nodes and column for the x coordinates and y coordinates, so MATLAB needs to know the number of nodes that is in your structure. For example, if I give a 4 by 2 matrix, MATLAB needs to understand that it has 4 rows in it. So it has 4 nodes associated with it, which means 4 nodes with x and y coordinates. How do I make MATLAB understand that there are 4 nodes in the structure? Using the size of parameter. Size of parameters of the node xy of the first element. For example, if you give you the this is one another command that you need to keep in mind. If you are just explicitly stating for the node vector, it will return you the parameter as 8 because you have 4 by 2, 4 rows and 2 columns, which means you have 8 elements. All I am interested in node xy vector first column. I am interested in knowing the size of node xy vector first column, which has 4 rows in it. So the size of the array is going to be equal to the number of nodes in the structure. So this is how I calculate the number of nodes in the structure. Number of elements. So number of elements is size of elements vector. So the elements vector, what do? You give you the connecting parameters. So for example, you say first element is between node 1 and 2. Second element is between node 2 and 3. Third element is between node 3 and 4. If this is the elements vector that you are giving as input, the size of elements vector gives the number of elements associated in this structure. So the size of operator has been used in this function to calculate the number of nodes and number of elements. So parameter that's different from the last week's script and this week's script is the degree of freedom parameter. So as I was saying, degree of freedom can vary from node to node but at this point of time, we will assume that the maximum number of degree of freedom associated with, let's say if a we are assuming the maximum case with 2 degree of freedom in each node, because we are not arriving at the 3D stage yet. So we can conveniently assume that degree of freedom for a 2D truss element, because we are developing this for a 2D truss element. So for a 2D truss element, for each node, the maximum degree of freedom is going to be 2 times the number of nodes. For example, for the structure, what is the number of nodes you have? For a square truss, you are having 4 nodes. So what is the maximum number of degree of freedom that can be associated with this? It's going to be delta 1 to delta 8, which means the number of degree of freedom is 8, which is 2 times the number of nodes. So this is how I am making MATLAB understand that the maximum number of degree of freedom that can be associated with a 2D truss element is 2 times the number of nodes in this structure. So when I say the maximum number of degree of freedom, because slightly when we are analyzing for right now, we are developing the stiffness matrix. We are not arriving at the force vector yet. The main purpose of developing stiffness matrix is to calculate displacement or calculate force from the unknown parameter. For unknown, we are going to calculate the unknown parameter from the known parameter using stiffness matrix. So we are having the freedom to disregard certain degrees of freedom, which we will be discussing in the future sessions. But at this point of time, I want you to assume the maximum number of degree of freedom for a node at this point of time is going to be 1 and 2, 3 and 4. So for a 4 node system, the maximum DOF variable, MATLAB is going to calculate it as 8. So I am initializing the stiffness matrix as a 0 matrix of size 0. 2 times the number of nodes, 2 times 4 is going to be 8. I am making MATLAB understand initializing the stiffness matrix as a 0 matrix of size 8 by 8. So and the another to concatenate, we discussed the control flow operators last week. The control flow operator has been for loop or while loop or if and else loop. You are free to follow any control flow operator, but I personally feel that for loop is slightly convenient in programming, and it kind of explicitly tells the one who reads the script what's going on in your script, unlike the while or if and else loop. This is my personal choice, and if you feel comfortable to code with while loop or if and else loop, you are free to proceed with the your own choice of control flow operator. So the control flow operator that I have used here is for E is the index variable. So I am looping it over from the first element to the n element. So first step I am doing is for each element, I am extracting the element nodes. For example, if you give me the first element, I need to know that the nodes associated with the first element are 1 and 2. Similarly, with the second element, it's going to be 2 and 3. And third element, it's going to be 3 and 1. This is where the order of numbering the elements and order of numbering the degree of freedom comes into place, because the element nodes, you are extracting the node vectors associated with the element, and then MATLAB just extracts the element variable per the input that you have fed to MATLAB, following your assumptions of counterclockwise or clockwise, so that like it follows a consistent loop, and then one element follows the next and one degree of freedom follows the next in the vector format. Similarly, node coordinate assumes the node xy of the nodes associated with the element. Node xy is the overall vector that contains the information x coordinate and y coordinate of all the nodes in the structure. But to develop the stiffness matrix for an element, you just need the node coordinates of the nodes associated with that particular element. So the element node coordinate extracts the nodal coordinates of that particular element from the overall node vector. So next big concept that comes here in programming is calling a function within the function. So here, as you can see, stiffness equal to axial element stiffness of DOF node coordinates E, A. I am not repeating these steps. For example, x coordinate, y coordinate, length of element, C cosine orientation, sine orientation, and then stiffness equal to EA by L cos square times sine square, or cosine minus multiplied by sine. I am not calculating these terms again. What I am doing here is calling a function within another function, nested function. So I am calling the function of axial element stiffness in the function that is called global stiffness matrix. So the global stiffness matrix calculates the stiffness matrix for the entire structure, but this is done for single element. I am calculating using the function that I have already developed before. So I have already the script ready. I am just using my current input parameters and I am passing to my old function to receive the output. So the next command that I am using is element degree of freedom. So why does the term element degree of freedom is important? So let me bring you back to this concept of order of numbering the degree of freedom. So for example, we discussed the third element which had degree of freedom delta 5, delta 6, delta 1, delta 2. This is an example that I explained to you on my canvas board. How are we indexing the stiffness coefficient terms? Let's say conventionally 5, 6, 1 and 2 do not follow any particular order. Like for example 1, 2, 3, 4, 3, 4, 5, 6, they follow a certain order. So you can make MATLAB assume that, okay, you assume from 1 to 4 or 3 to 6. While you are programming, you can make MATLAB assume 1 to 4 or 3 to 6 for the element 1 and 2. But when you come to the third element, you will get stuck because there is no way that you can write a general script that will make MATLAB assume the index 5, 6, 1 and 2 without the concept of element degree of freedom. So when we take the element vector which says the node information, for example, I will explain it to you with an example once I have explained to you the script. So the element vector has the node connecting information. So it's going to be 1, 2. Element 1 is between 1 and 2. Element 2 is between node 2 and 3. Element 3 is between node 3 and 1. This is what your element vector is going to be. So element DOF is going to take the element vector. So for example, here your element DOF for the first element is going to go to the element vector first array. So what your element vector array first row is going to say is the first element is between the node 1 and 2. So when you have understood that the first element is between node 1 and 2, you make your element DOF variable calculate that what I am saying is stiffness matrix of element DOF. So which means K of 1 to 4 is this matrix. For example, when I was saying K11 to K44 for the first element, K33 to K66 for the second, K55 to K22 for the third element. So that's where the element DOF comes in the big picture. So element DOF is a variable that calculates the degree of freedom associated with each element that is calculated from the element vector that you give as an input to MATLAB. For example, let me clear my MATLAB commands and then let's start fresh. We have global stiffness matrix as the main function. So let's declare the input variables first. Node xy is the vector that contains all the node information. So for easy understanding, let's assume a square truss, which I was explaining to you throughout the session. To be consistent, let's assume a square truss. And then the first concept we are going to follow while giving the node information is we are going to follow a counterclockwise assumption in naming our node vectors. And I am starting with 0, 0. And then the next node is going to be 0, 4. And then the third element is going to be 4, 4. And then the fourth node is going to be 4, 0. So this is my node vector. And the elements vector. So we have numbered our nodes in the counterclockwise direction. Let's stick to the same assumption and number our elements. The first element is between 0, 0 and 0, 4. And the second element is between 0, 4 and 4, 4. So your first is going to be 1, 2. The second element is going to be between second node and third node. And your third element is going to be between 4, 4 and 4, 0. That's between third node and fourth node. And your fourth element is going to be between fourth node and the first node. So this is your elements vector. And we can assume the Young's modulus and area to be uniform at this stage. So this is a basic, I'm giving you conceptual basic way of developing the global stiffness matrix. You are free to expand this script to associate each element with each individual area, and then each element to have the elasticity should be same, but the area you are free to expand as an area vector and then associate each element to have its individual area and use that for calculating its individual stiffness matrix. But to have it simpler in the initial stage, I am assuming the uniform area for the MATLAB script. So let's get started with the main function, global stiffness matrix, and my input is going to be node xy, which is the variable vector we have defined now, and elements, which we have defined now, and then Young's modulus of elasticity, and then area vector. So the another point or another concept that I wanted to bring to you at this point of time is, should this variable name node xy and then this variable name node xy, should they be same? I would say so, they need not be same. You are still convenient to follow. For example, I can give this as node ABC and then still pass this as a parameter. Node xy will assume the values of node ABC. But the one variable that you need to be consistent is with the return variable of the function. If you say the function stiffness matrix returns a global stiffness matrix of so and so, your return variable should be defined as stiffness matrix. Or you can also develop a MATLAB function without calling a return function variable, and then you can define that in your local script and then call your function. For example, you can define your return variable while you are scripting your main function, or you can do it in your function module. These are all your the freedom that you can enjoy as a programmer in MATLAB, which I highly recommend you to explore and learn how it works. Even if you run into errors, MATLAB has a system of debugging resources which will help you to come out of that error. Yeah. So as you can see, the global stiffness matrix for the square truss, each element we developed a 4x4 matrix. So even if we add individual 4 elements, we should have arrived at a 4x4 matrix. But what we desired was an 8x8 matrix. Had it been we had simply added the matrix, we would not have arrived at this 8x8 matrix in MATLAB. So with the concept of concatenation that we discussed today in session, and then the algorithm that we developed, we implemented that in the MATLAB script. So we developed a 8x8 matrix.